Topics 8.3 to 8.4, population growth. To help you study, I've put together a checklist that tells you exactly what you need to study in AP Bio Unit 8, and in fact, all of AP Biology. To download it, go to apbiosuccess.com/checklist. What are the 4 factors that directly change population size? If you had driven into my home city, Berkeley, California, a couple of years ago, you would have seen this sign listing the population at 112,580. It's now a little bit bigger. What could cause that to increase or decrease? There's only 4 factors. Those are births, which increase the population, deaths, which decrease it, immigration, which increases population size, and emigration, which decreases it. For AP Biology, one of the most important concepts to understand is exponential growth and its limits. Exponential growth is a pattern of population increase in which the population size doubles at a consistent rate over regular time intervals, resulting in rapid and accelerating increase. Why? Because the growth of the population is proportional to the amount already present. In this growth curve over here, the rate isn't changing. It's continuing to be at 140%. But when there are 1,000 individuals, the number of individuals added over a period of time is going to be much higher than it was when there were 200 individuals. The basic idea is that in exponential growth, the bigger the population, the bigger the increase. Exponential growth is based on a mathematical model, and that's something you need to understand for AP Bio. Then you don't need to memorize it. There's a formula sheet. The formula is delta n over delta t equals r times n. And in this formula, n represents the population size, t equals time, r is the rate of increase. So in plain English, the change in population over time equals the rate of population growth times the population size. In biological systems, when does exponential growth occur? It occurs when a population has ideal resources and nothing is slowing down its rate of growth. This can be the arrival of an invasive species, the early phase of a bacterial infection, the early phase of an epidemic or pandemic. So it's always ultimately limited because nature is finite, but during this phase when the population has ideal growing conditions, exponential growth can occur. That's what occurred early during the coronavirus pandemic. This shows one country, Brazil, 2020, and you can see this exponential growth curve as the virus entered the Brazilian population and spread from individual to individual. Exponential growth. Exponential growth is related to the idea of biotic potential, and that is the maximum rate at which a population can expand, and you can see it represented by the letter R sub max. That represents biotic potential. Your success in AP Biology starts here. Are you struggling with AP Bio? With learn-biology.com, students get the skills and confidence to be a top student and earn 4s and 5s on the AP Bio exam, guaranteed. Go to learn-biology.com to find out how you can master your biology course and crush the AP Bio exam. Exponential growth can't continue forever, and ultimately it's limited by the environment's carrying capacity. That's represented by the letter K. It's this dotted red line over here, and it's the maximum number of individuals that a particular environment can support. It's caused by limiting factors, factors that limit population growth. As a population approaches its carrying capacity, there's increased environmental resistance. The environment starts pushing back against exponential growth as density-dependent limiting factors slow and then stop a population's growth. Density-dependent limiting factors are exactly what they sound like. These are factors that increase in intensity as a population approaches K. As the population grows, its density, the number of individuals in a particular area, is going to go up. That's when these density-dependent limiting factors kick in. They include competition between the individuals in the population for resources. Parasitism, parasites that are parasitizing the individuals in the population, and it gets easy for those parasites to spread from one individual to the next as the population increases. It gets easier for predators to pick off members of the population as the population increases, and it becomes more stressful for the individuals in that population, and that tends to lower their rate of increase. To incorporate the effect of limiting factors and carrying capacity in our understanding of population growth, we need a more sophisticated model. That's the logistic growth model, and it's represented by this formula over here. It shows how a population's growth rate decreases as the population's number approaches its carrying capacity, or K. And it's represented by the formula delta n over delta t equals the growth rate times n multiplied by this expression, k minus n over k. N is the population size, t is time, r is the rate of increase, and k is the carrying capacity. Let's plug some numbers into this logistic growth formula and see how it actually works. In this example, k equals 1,000. That's our carrying capacity over here. But let's say that our population is 10. If n is 10, if that's our population size, then k minus n over k is 1,000, that's k, minus n, that's our population, divided by the carrying capacity, 1,000. That's 990 divided by 1,000, that's 0.99. Growth looks exponential because whatever our rate of growth would have been, we're multiplying it times 0.99, will be in our exponential growth phase. But if we increase the population to 900, then look what this does to this expression, k minus n over k. It's now 1,000 minus 900 divided by 1,000, k minus n over k, and that's 0.10. So whatever our rate of growth would have been over here, we're now going to multiply it by 0.10, and that's going to cause growth to quickly level off. As we get to k, as population is equal to the carrying capacity, then population growth stops altogether. Those density-dependent limiting factors that are part of the logistic growth model that characterize carrying capacity can be extrinsic or intrinsic. Extrinsic factors come from outside the growing population, and it includes things like predation, parasitism, competition. Intrinsic factors come from within the physiology of the growing population, and it's usually about stress caused by increased crowding and competition between individuals in the growing population, and that lowers the birth rate. Limiting factors can also be density independent, and these are factors that are unrelated to a population size. They're not related to the population's increasing density. So examples are things like hurricanes, floods, earthquakes, human-caused environmental disasters like an oil spill, a toxic chemical release. All of those have nothing to do with the population, but for example, there was a population of birds that was living within these trees. Well, its population is going to be vastly reduced by the damage that's caused by this storm, but that had nothing to do with whether there were a lot of individuals or just a few individuals. It's outside the population's density. It's density independent. Are you asking yourself, how am I going to get a 4 or a 5 on the AP Bio exam? It's a good question because it's a hard test, but we have a plan for your success. Go to learn-biology.com, sign up for a free trial, and complete our interactive tutorials and interactive AP Bio exam reviews. We guarantee you a 4 or a 5 on the AP Bio exam. See you on learn-biology.com. So to check your understanding, take a look at this graph, which shows the results of a student experiment where they're growing duckweed in a cup. This graph is from learn-biology.com. It's part of an FRQ, or a multiple choice question. This is what duckweed looks like. And the question is, in this graph, I'd like you to identify carrying capacity, I'd like you to identify the exponential growth phase, and I'd like you to identify where you see density independent regulation. So pause the video, do that, and then see my answer. Carrying capacity is over here at B. You can see that there was an exponential growth phase and then it levels off. That's got to be carrying capacity. The exponential growth phase is over here at A when you have the J curve of growth. And density independent regulation would be at letter C. How do you know? Because here's the population. It's growing just as it is over here, but then at this point, something abruptly stops population growth. That didn't have to do with the density. The density dependent regulation kicks in over here, so that had to be independent of density independent regulation. What happens as a population reaches or surpasses its carrying capacity? I'm going to show two scenarios, there are probably more. One is oscillation. You have a cyclical overshoot of the carrying capacity and decline, and that's caused by a reduction of resources and then recovery. So here's a population that's grown beyond its environment's carrying capacity. That caused somewhat of a degradation of resources, and that reduces, for example, the food supply, so the population falls a little bit. When it falls, the carrying capacity recovers, and then the population rises, slightly overshoots, and then falls, and that goes on and on. That is different from what's shown on the right, which shows a catastrophic overshoot. The line in blue represents the population of deer. The line in green represents the shrubs that the deer use to forage and to supply themselves with food. Well, in this case, there's a catastrophic overshoot of the carrying capacity, and that causes essentially an environmental collapse, and the population of shrubs crashes and the populations of deer crashes, and there's no subsequent recovery. We have serious environmental degradation. Another population growth pattern to know about for your AP Bio class is about predator-prey population cycles. Here's an incredible data set that shows the population of lynxes, cat, that's a predator in North America, and hares. Both of these animals live in Canada. Both have great data sets because their pelts were collected by trading companies that were active in Canada in the 1800s into the 1900s. So we see this kind of oscillation. What's going on? It's partly explained by density-dependent regulation of the hare population by lynxes. The lynxes are the predators, the hare is the prey. As the population of hares goes up, that provides more food for the lynxes. Their population goes up. They eat more of the hares. The hare population declines, and then the lynx population declines. But when the lynx population declines, there's less predation on the hares, so their population increases. But that's only a partial explanation. What's also going on is that there's cyclical oscillation of the hare population by food availability. So they're herbivores, they're preying on plants that are available in this area, and they're competing with one another. So cyclical oscillation of the hare population by food availability and interspecific competition, which in turn affects the lynx population. Everything is complex. That's what makes biology so fantastic. Here are your next moves for AP Bio success. Please subscribe to learn-biology.com and please watch this next video.